Welcome to the first video in my series on multimodal embeddings. In this video, I'll talk about what they are, how to generate them with Python using Clip, and how to use them for e-commerce product search. We'll demonstrate the e-commerce use case by creating a ranking model for products based on a search query. Unlike conventional product search, our approach will use purely embeddings as a way to score similarity between the text and the images. And for this, we'll be using Clip, an open source model developed by OpenAI, which is capable of producing image and text vectors that are in the same embedding space. Honestly, these demos that I've been putting together for this multimodal embedding series, they feel like some of the coolest stuff that I've ever done with machine learning. I really got a lot of those oh damn moments when I was creating these, and I hope that'll come across a little bit in the video. Of course, you're welcome to follow along. I'll start things off with a quick demo. By the way, I'm Alex and I'm a data engineer. And here on ZazenCodes, I teach full stack data science. If you're interested in supporting the channel, you can check out my premium content on Patreon, and you can sign up for my newsletter. I just send one email a week to go along with my new video launch. I would encourage you to download the source code and follow along with me. You can grab it off of GitHub and you can just say git clone and just paste this in here. Once you do that, you can go into the ZazenCodes YouTube folder and then source and then multimodal embeddings. And this is where you're going to find all of the source code for this video. The first thing I'm going to do is set up my environment, and I've got this requirements file. There's a lot of pretty intense libraries in here, so some of these might give you problems and you might want to install things individually in that case. So using tmux, I'll open up a new pane and I'll create a new virtual environment, pip install -r requirements like this. In my case, you can see it's using cached versions of all of these libraries, so this ran really fast for me. But for you, you'll have to download all of these from the internet, so it'll take a lot longer. Now I'm going to open up a Jupyter notebook using VS Code. And as you can see up here, I've got a bunch of notebooks available, and a lot of these are the ones I've been using for development. So we're going to start with this part 1 image text clip embeddings notebook. We're going to be using the transformers library to load the clip model and the clip processor. The first time I try and run anything, it's going to ask me to pick my environment. Here's the one that I just set up, this multimodal embedding, so I'll select that one, and then I'll be prompted to install the right package so that I can run Jupyter Notebook with Python in that virtual environment. And then I'm good to go with running this. I'll have to zoom out a little bit. For me, this pulled really quickly, and that's because I have this cached, and that should be in this cache folder in your home directory under Hugging Face like this. And you can see a data sets and a hub, and if I look in the hub, I'm going to see this here. And it'll be under this OpenAI clip right here, and I can make that really obvious just by piping this into a grep for that pattern, and now we'll see that here. So this is my model. I already have this cached. If you don't have this, it's going to have to pull that, and it'll put it right there on your computer. So now we have this clip model. I could also do this, say, dir method on it in order to see all of the things I can do. Here there's one called parameters. There's named parameters. There's number of parameters. Let's look at the number of parameters. 151 million parameters in our neural network model. So now I'm going to bring in some functions for actually creating these embeddings. And the first one I'm going to look at is a function to get a text embedding. Here's how that looks. We're going to take our clip processor. That was one of the things that we imported above here. What this does is it prepares data to be in the right format for inputting into the model. So I can just take in some text, which is going to be a string, and then I can feed that into my clip processor. I want to return PyTorch tensors, which is why I'm saying PT, and padding equals true will allow my text, if I have multiple text elements, to be of different lengths. We're going to need this later in the series. Then I'll generate my text embeddings by putting these through the model and asking to get the text features for these text inputs. So I could try that right here with just some random string of characters, and I get out this ginormous tensor of my embedding. Here's the function to get an image embedding. And actually what I'm taking is an image URL, which is also a string, and this is going to be something on the internet. So for this, I need the requests library. And I'm just setting this header because Wikipedia was giving me a hard time, and I was feeding in Wikipedia pages for this. In any case, I'm just getting this image. This goes ahead and opens it like it's a file type object. You could load something in here from your system if you wanted instead. Like for example, you could just say like this. But I want to do it this way. Then I'll feed this image into my clip processor, again returning this PyTorch tensor, and asking for the image embeddings for that image. So let's try that now. I have this image from Wikipedia, and I'm going to get its embeddings in this way. I never defined image compil import image. Now I'll be able to run this, and I get that it is 512 numbers in there. Let's look at what this image is. Import image, display image, because we already have image defined in our namespace. So this is what we're looking at. Okay, I want to put a pin here. So I'm going to say copy into new window. And you can actually do this. Open up the same notebook in multiple places with VS Code. Pull that in a little bit. This looks like a man in a red toga saying bye to his family. So let's grab the text embedding for that. Look at the cosine similarity of these things. There's a way to do the cosine similarity with torch. And so I could just say import torch, which is PyTorch. Then I can access torch.nn.cosine similarity. Give me a callable, so I can pass in, say, the text embedding and compare that to the image embedding. So I get the cosine similarity in this case is 0.3179. Now, we know that cosine similarity can be from -1 to +1, like I talked about in my last video. The cosine similarity gives us the cos of the angle between these two vectors in our embedding space. And cosine itself can range between -1 and +1. As you can see, the cosine similarity derived from this function here, where the dot product of two vectors is equal to the magnitudes of those two vectors multiplied by each other times the cos of the angle between them. So we just solve for cos of the angle like this by evaluating this function here, a dot product with b, and then normalize it by the length of those vectors. So this is all we're doing with this equation right here, where we get the cosine similarity between these two vectors. Let's try some other texts here. Birthday party grandma. And that yielded a significantly lower score, indicating that that content is less relevant to the image. Airplane, remote island. Nice, that one's even lower similarity. And the last thing I want to just show you are what these actual embeddings look like. So let's just grab the text embedding for the most recent example. We get this vector out here. What I could do is plot this. Import seaborn sns.hist plot of this, and I'm going to send it to a list so that it'll be able to plot that well. And we can see that our embeddings are mostly between -1 and +1. These have been normalized somehow. Of course, the mean is going to be close to 0. The standard deviation in this case is 0.38. And lastly, I want to get the length. Look at this square, the square of each element. Just want to confirm that by, I don't know, I'll get the shape. The shape is the shape I'm expecting. Sum them all up. This is not quite the length because I need to take the square root of this. This is a PyTorch object, so I'm able to like call these nice chain methods on it. And so I'm getting that my length is a little bit less than 10. Also notice how it has this grad function equals square backwards or standard backwards. PyTorch, with every object that it has defined, is interested in calculating the gradient of that thing, so the rate of change with respect to some other parameter. And it does this so that it can train neural networks. In this case, there's no relevance here. We don't really need to keep track of this, and there's probably a way of saying, don't worry about it. You don't need to keep track of the gradient stuff for this number. What we could do is just get the item here, and then that's going to just return this as an actual number. And I could say get the type of that, and it's a float type. Let's take a step back, and I'll introduce the clip model and talk about how it was trained and what it does. And then I'll set up our main demo for today, and we'll get right into that. By the way, I have another video on generating text embeddings with Python. There I use Word2Vec, BERT, and an OpenAI model provided by their API to get text embeddings. It's a good warm-up for this video series, and you can find a link to that in the description, or I'll leave a link at the end of this video. So as you saw, multimodal embeddings are a type of data representation that can capture information in a shared vector space from multiple modalities, such as text, image, or audio. And this allows us to perform tasks like comparing these modalities to each other. So how does CLIP allow us to do this? It stands for Contrastive Language Image Pre-training, and it was trained on 400 million image text pairs. The contrastive part refers to how it was trained. Its objective is to bring corresponding image and text embeddings close together in the shared embedding space, while at the same time pushing apart the embeddings for non-matching pairs. It uses a dual encoder architecture, two separate neural networks, one for image processing and another for text processing. And these networks transform the inputs into embeddings, which are high-dimensional vectors. As we saw earlier, there are 512 dimensions. Coming back to this idea of contrastive learning, let's consider what happens with CLIP for a given batch of data, so a given bunch of images and their text pairs. The model will compute the similarity for every image and every text embedding in that batch. This similarity being the cosine similarity that I discussed earlier. And then it computes the loss function, this contrastive loss, which encourages the similarity score for matching image text pairs to be higher than the similarity score for non-matching pairs. And then using something like gradient descent, it updates all of the parameters in the model so that on the next iteration, it does a better job at this objective. And then it continues doing this until the model parameters, we saw earlier there was like 150 million of these, are optimized. We access CLIP using CLIP model and CLIP processor, which are Hugging Face libraries. These serve different purposes. The CLIP model object is the core model that contains the neural network for both the image and text encoders. And it's the thing that's responsible for generating the embeddings from input data. The CLIP processor is a utility that helps process input to make it suitable for the model. So for text, it tokenizes the sentences, and for images, it resizes and normalizes them. And lastly, we're going to be using PyTorch in this series of videos. PyTorch is a deep learning library that uses tensors as its core data structure. They have optimized storage for your memory. They can also put that storage into GPU instead of using your CPU. And they have additional considerations which are specific to deep learning, like that gradient thing that we were talking about earlier. Let's get into the core demonstration for today. We're going to be creating a product search for an e-commerce website that sells shoes. What we want to do is be able to search for some term and then compare that to all of the images in our database and source the most relevant shoes for that term. But crucially, we're not going to be considering product descriptions or product titles of any kind. All we're going to be doing is taking the text embedding for our search term and comparing that using the cosine similarity for the image embedding for each image in our data set, and just pulling all of the images that have the highest similarity. This is purely using CLIP's semantic understanding of image and text and using embeddings and their similarities to source our results. This is not something that you see commonly on websites when you're doing product search, but I think there's huge potential to actual ecom business with this use case. So let's get to it. And first we're going to pull our data set. We've found a bunch of shoes on Kaggle, and let's grab that in our notebook. Here's the data set I'm referring to, e-commerce product images. This data set's about 400 megabytes. You can go ahead and download it here from Kaggle, and we can see a bunch of examples of them right here. There's going to be about 2,000 images in our data set. For me, I can load all of the images I want using this code here, and if you want to do this with your notebook, you'll just have to download the source data and put it in this data folder. And the data folder I'm referring to is right here in my multimodal embeddings. It's called data, and inside of here, we're going to find all of the source data for the demos in this video. This one's just in something called fashion images. That's what I called the folder. Right, so I have 1,500 images. In order to run this next chunk of code, I need NumPy, and I'm also using a function here called batched. That's available on more recent versions of Python, and I can say from itertools import batched. If I just look at the docs for that, it batches data into tuples of length n. So it's really straightforward. I have some list here, and I just want to batch that in, say, chunks of 3, and it does that for me here, where the final batch is going to have less than 3 items. In this case, I'm using that in order to batch through my images in chunks of 500, so that we don't run out of memory when I'm creating my embeddings. This code also depends on this getImageEmbeddings function. I have a function to get a text embedding This has our model and processor baked into it, and then it just grabs the inputs for that text like we were showing earlier and returns the text features or the embeddings for that input. And down here I'm doing the same thing with images. It's exactly analogous, except I put the images through some transformation, put them into a new size. I need this transforms and this read image function, and these are available from PyTorch, in particular this Torch Vision library. I'll also go ahead and import this make grid function, which we're going to use later. Now I have all the functions I need. I'm just going to run this code here, and I can start batching through my images to get my image embeddings and then save them to my disk. Inside of data fashion images, I have this embeddings folder, and I've already created these and they've already been saved to my disk, but we're going to recreate these now. So I'll just clear these out. And I'm saving them as PT files, which is PyTorch. That's the convention when we're using torch.save, and I'll be able to load these later. So let's get this running. Now I have all of my embedding files here, and I can look at them on my system. They're each about 1 megabyte, so the data is really not all that big, but it's nice being able to run this computation ahead of time, and then I can just load them later instantly. And the way I can load them is by using torch.load. And after loading all of them in this loop, I concatenate them using torch.cat. And the result is that I get an image embeddings vector with this shape. So I have about 1,500 samples, and each of them have a dimension of 512. And these are our clip embeddings. So if I say print the first one, it's going to look really familiar to what we were seeing earlier. So now we want to be able to rank all of these images with respect to some text embedding. And here's a function that'll do that. I take in some text embedding, which is going to be a torch tensor. And then I take in image embeddings. These are also going to be a torch tensor. Then I'm just defining my cosine similarity scoring function. Call that for the text embedding with our image embeddings. The reason I have to unsqueeze my image embeddings so that they match the text embedding shape is because I'm iterating over those with this loop. All right, so let's try this. And I want to get my text embedding for something. Let's just say like red, pass in my image embeddings, which I have loaded. Let's see how this goes. So this ran pretty much instantly, and the scores I get out look like this. So now the way to actually sort our items is using numpy.argsort on my scores, and what this is going to do is it's going to label the indexes of the sort order. So the first element just happens to be the 398th item if these were sorted. So if I took the scores as a numpy array like this, then what I could do is index that using the argsort scores like this. And using the Zen of Python, we would think this is a little crazy, so I'm just going to label those as a variable like that. And now what this is going to do is provide the scores in the right sorted order. And you can see that happening just like looking at this representation where we have the lowest scores at the front and the highest scores at the end. So I would want to flip this around like this, but I want the actual images themselves. So what I could do is just copy this. I'll keep the first line the same, but in the second line, these have to be the images. And now I'm getting the image pass with the proper scores. So let's say for image in, and I want to iterate over a few of these. And I'll say print the image. These are the first 5 images. I want to actually display those images. Display image of this image. Seeing a bunch of big red shoes here. Width equals this. Keep them really tiny. All right, so here's a bunch of red shoes as we expect. Though that's pretty cool, but I want to see these in a grid format. And so I have a chunk of code that will do that. And it's using this transforms.toPillImage, and then I'm feeding in a grid, which I get from this make grid function. I imported this earlier from Torch Vision. I'll show you where I did that. It was right here. So I'm using this torchvision.utils make grid. All right, coming back down. So if I go ahead and run this, now I'm getting a grid. By the way, this was that moment where I'm like, oh shit, this stuff works. And I was pretty excited. So let's bundle this code up into a function that I can call for various search terms, and we'll test out a few things. You'll remember that this is what our rank items looked like, but I was doing something really weird where I actually iterate over all of my image embeddings. I don't think I really need to do that because using Torch, I can just do vectorized stuff. So what I actually want to do is grab all of the scores in one shot, and with these image embeddings, I don't need to unsqueeze these because they're going to be in the right shape. I don't really need to iterate or anything like that. I'll just go ahead and return these just like this. So if I call that, I'm just getting this giant tensor out with all of my scores in it, which is exactly what I expected. Right. right, so I'm a little bit happier with that. And now I'm just going to generate this product feed using a function here. This is the same code above where I'm doing this grid, but now I've wrapped it in display. That'll display it inside of this function for me. And then I'm going to return the ranked images. So I'll have access to those actual images, as in the like files, if I need to reference them for some reason. Otherwise, what this does is it just takes in a query. It calls that rank items function, and I get out a bunch of scores, which this is actually going to be a tensor now. So we'll have to sort of make sure that this works still, because I haven't actually tested that. My image embeddings, which I'm passing in, that's used to rank my items. Then I just get the sorting, resize all of the images, read the images using torch vision again, feed them into this make grid function. Let's test this out. Let's try blue. Let's give this a shot. Not happy actually converting that tensor to a NumPy object. And this was that change I made up here. Say to list. Now it's going to just return a big list of numbers. Now when I run this, hopefully everything works. And it does. We get a bunch of blue shoes. Let's get all the lemon shoes. If you type that into most websites, you probably wouldn't get anything back except maybe products that have lemon in the name or brands that have lemon. But here what it's doing is it's getting me shoes that look like a lemon. Let's try this one. The lightweight images. Okay, so these shoes do look pretty lightweight. A lot of them are like a smaller form factor. Let's get all of the shoes related to work. So it's interesting. Some of these are like construction site work. Some of these are business type work. Some of these are like sport type work. Let's try that. Okay, these are all pretty good. I think you'd be able to do sports in most of these. How about just soccer? Okay, these all look like soccer shoes. One thing I might want to ask for is fancy shoes. Nice. Okay, these all look really fancy. What if I was a man? What if I said fancy man shoe? Okay, great. So man really picked up on the male type shoes. All right, what about scary shoes? This first one definitely looks pretty scary. Here's a cool one, explosion. I could see it. Some of these definitely are resembling a bit of an explosion. We have shades of yellow, we have shades of red. This picks up on a key point I've been noticing, or a trend here, where the color of the thing that we're searching for is really prominent in the response. One example I really like to illustrate that is this one, where I search frozen. And you can see a lot of sort of these turquoise shades and blues and whites. If I search frozen here, we're going to get a bunch of pictures of the Disney movie. And these have kind of the exact same colors that we're seeing in the response. So the language model understands that these colors are associated with the word frozen, and it's showing those colors in the product response, which I just think is so cool. I just got a couple more. This one is glass. And if I search Cinderella, we obviously associate that shoe with Cinderella. And we're getting a lot of shoes that would be like a good candidate for this Cinderella shoe. And here's another interesting one. If I search Dorothy, in the context of shoes, we have that sort of red slipper, right? Or Dorothy's slipper that she leaves behind. And we're getting like exactly those images here. So that concludes our first demonstration on multimodal embeddings using the clip model with Python. If you enjoyed this video and want to see more like it, then please give me a like and consider subscribing. You can also check out my content over on Patreon or sign up for my newsletter for free to support the channel. To recap, we used the Transformers library from Hugging Face to load the clip model using Python in a Jupyter notebook, and then we created image embeddings for a bunch of pictures of shoes. We worked with these image embeddings as PyTorch tensors and compared them to text embeddings also created with that clip model, and compared them for their cosine similarity. When we found the most similar images to the search queries that we were looking for, we returned those in a product feed-like grid in our Jupyter notebook. And as such, we created an e-commerce product search ranking model right here on our machines, just using embeddings and this awesome clip model that OpenAI has trained and provided for us, open source. In the next video of this series, I'm going to bring a third modality into our embedding space, which is audio. And we're going to see how well we can match image with text and audio using these environmental sound recordings and a brand new data set that I actually cooked up myself for this purpose. Then we're going to look at video embeddings in the next video, and the final video in this series will cover fine-tuning. Each video builds on the previous one. If you want to carry on to that audio embeddings video, there's a link on the screen here, or you can find links to all of the videos in this series in the description below. Thank you for watching, and namaste.